Hello, this is Dimitris Stamatellos, and I'm going to talk to you about how we can form planets around M dwarfs by disk instability. One of the striking features of the observed exoplanets is that their properties are very diverse. In this graph, I plot the planet mass versus the semi-major axis of the observed planets, and you can see that they are scattered all over the place. These exoplanetary systems are nothing like our solar system. Many of the exoplanets observed orbit around M dwarfs, that is, stars with mass less than 50% the mass of the Sun. These stars are the most common type of stars in the galaxy and in the universe. Many of these planets around M dwarfs are more massive than Jupiter. So there are systems that have, let's say, a 10 Jupiter mass planet orbiting a 100 Jupiter mass star. That means that the initial disk mass of that form in which these planets formed was at least 10% the mass of its central star. And this mass could have been much higher if you consider that a proportion of this disk could have lost due to photoevaporation or disk winds, or indeed accreted onto the central star. So when you're talking about disk to stellar mass ratios, about 10 to 30%, it's a region where gravitational instability can operate and form planets. So we decided to study the process of disk instability around M dwarfs by three-dimensional radiative hydrodynamic simulations. So we performed 27 simulations in which we vary the mass of the star, the radius of the disk, and the disk metallicity. And we used the technique of mass loading, in which we started with a low mass disk and increases mass gradually until fragmentation occurs. And this is in order to match the inflow of material and the growing of the disk, inflow of material from the surrounding envelope. These are the results of the 27 simulations. In this graph, I plot the disk mass versus the stellar mass for different initial disk radii. And you can see, let's focus on for a minute on the green dots. For a 90 AU disk, the mass needed for fragmentation increases with the mass of the settler star. And this happened for the other dots for the larger disks, the blue dots, and the smaller disks, the red dots. So the smaller the disk, the lower mass needed for fragmentation. But we also see that the mass, the disk to stellar mass ratios needed are quite high. And these are plotted here against the disk radius, initial disk radius, and also we also note here the metallicity of the disk. So we can see in the top of the bottom left corner of the graph, we need mass ratios of at least 0.3, maybe up to 0.4 for disk fragmentation to happen. And lower metallicity disk, higher metallicity disk need even much higher disk to stellar mass ratios. So it is the question remains whether the disks indeed exist at the initial phases. So we're talking at very early stage disks, so like HL tau, but much younger disks around lower mass stars, of course. In our simulations, we followed the evolution of these fragments that form the disk through disk fragmentation. The collapse of the fragment, going from a fragment to what we call a protoplanet, the initial planet in the disk, goes through different phases. So if you look at this graph, here I plot the temperature of the center, at the center of the clump of the fragment versus the density. Initially, starting here, the collapse is more or less isothermal. The fragment is optically thin, so energy provided by the collapse is radiated away. And then at around this density, 10 to the minus 12 grams per cubic centimeter, the fragments become optically thick and they start to heat up. And then this heating with a gradual increase of the density continues until the temperature reaches about 2000 K up here, when molecular dissociation happens and the second collapse occurs. So here you have the first collapse and the formation of the first opaque core, and then the second collapse that forms the protoplanet. And the phases that these fragments go are similar to the phases of collapsing one solar mass core. The red line here corresponds to what happens at the center of one solar mass core. So the process of forming a planet in the disk by disk instability is in effect the same the process that forms stars in much bigger systems. And we have very good resolution. Each of these fragments is represented by about 100,000 particles, SPH particles. So we're able to calculate the properties of these fragments. So here I have, I plot the density versus radius. So the fragments are more or less about 1 astronomical unit or maybe a bit bigger. And the temperatures you see at the center, they're very hot. Their temperatures about 10,000 K. And then the temperature drops down to about 10 to 50 K after 1 AU away from the center. So these temperatures that we calculate are similar to the temperatures found by models around in the accretion shock around planets formed by core accretion. So the temperature cannot really be a distinguishing factor between the two models. And then I also calculated the sizes of the first and the second core. So the second core, we can think it as a very bound object that cannot be disturbed, where the first core is a bit less loosely bound, more loosely bound. So these outer layers of this protoplanet may be disrupted by, let's say, tidal interactions. And to calculate the sizes of the first and second core, we can look at the infall velocity of the clump. So initially, if you start from here at about 10 AU, the gas flows onto the fragment, then it slows down the accretion shock around the first opaque core, and then inside the fragment, the velocity increases again, the gas infalls towards the center of the clump, and then you have the formation of the accretion shock around the second core. So this is about a fraction of an AU. So this is more kind of like the size of a planet. So I plot here the first core and second core mass. The first core mass varies from about 5 Jupiter masses up to 20 Jupiter masses, and lower metallicity cores, the red ones here, have smaller mass than the higher metallicity first cores. And then we also plot the second core mass, again with respect to the distance from the star that they form. And again, you see that the red dots, the lower metallicity cores, have lower masses, about 2 to 3 Jupiter masses, going up to 5 Jupiter masses for more metal-rich disks. And this, basically, these are values you expect from objects formed by disk instability. These are corresponds to the opacity limit for fragmentation. And then we went on to compare these properties with the observed properties of exoplanets. So we put them in the planet mass versus distance from the star graph. As expected, these planets formed by disk instability occupy the white orbit high mass region of the graph. And I plot here both the second cores, the stars, and the first cores. But of course, we need to remember that in order to make a useful comparison, we need to evolve these protoplanets within the disk. So these are the properties of these protoplanets when they form the disk, not after a few gigayears, where it's correspond to the properties of the observed exoplanets. So we need to remember that there may be migration that may push these planets inwards or throw them outwards. There's gas accretion from the disk that may increase the mass of these planets. And finally, there may be tidal downsizing that may reduce the masses of these planets. And at the moment, we're working more on this evolution of these fragments, trying to understand what their final properties will be. So to sum up, so that this fragmentation can happen around M-dwarf disks to form protoplanets, but really high disk to stellar mass ratios are needed, about at least 30%. But observations of very massive planets around M-dwarfs show that this high disk to stellar mass ratios may be attainable at the early phase of the disk. These Jupiter mass fragments, these protoplanets that form in the disk, go through the first and second collapse phase, just like the solar mass counterparts, and form protoplanets very fast, within a few thousand years, that are very hot. Their centers are about 10,000 K. And finally, in order to determine the final properties of these planets, we need to further follow the evolution, and to determine the disk protoplanet and protoplanet interactions. So thank you very much. I hope you enjoyed the talk. If you have any questions, let me know. Thank you.